Okay, so I think Andrei and I are the only people who are not going to be talking about whales. So this is a bit of a different talk. But essentially, you guys have all been talking, and you guys are the experts on a lot of the different steps that the Halo project and kind of on Southern Residents and Killer Whales in the Salish Sea generally. And Andrei and I are part of a team at SFU, and it's kind of our job to build the underlying background infrastructure over the next few years to actually connect those things together. So that's the context with why we're here today, not talking about whales. But I'll pass it over to Andrei for the first little bit. I'm hoping that we can hear him and see him. So I can say it.
Thank you, Jillian. Hello, everyone. My name is Andrei. I'm Software Research Development Manager at RCG. So you may ask, what's RCG? Well, glad you asked. RCG stands for Research Computing Group, and main goal of the group to assist researchers with high performance computing platforms and other digital research infrastructure, both locally, regionally, and nationally. Our software development team is fairly new. It's been created just over 2 years ago. We started as just a small team of 2 developers and myself, and now we have a team of 5 and going to bring 3 more developers on board by the end of this year. The initial goal was to create the software development program that will start that will pair the SFU lead research projects with RCG software development team to develop custom software and platforms using best development practices that will help accelerate research outcomes and result in more sustainable and stable software solutions. So our team provides software tools to researchers to reduce time to discovery, allow researchers to make effective use of the digital infrastructure, promote reuse of the tools to minimize the cost of the software development prior to the start of the research, and create a community of research software developers to further accelerate research through collaborative software development and expertise sharing. So far, we completed 8 projects and have 5 ongoing projects. And we'll be happy to work with all of you on a Halo project. So next few minutes, I'm going to show a very brief demo of one of our projects called Natural Hazard, and discover similarities and differences between Natural Hazard and Halo projects. So in brief, Natural Hazard projects are meant to detect and monitor many hazards. And when the threshold is met, communicate information directly to the community decision makers and emergency responders. So here's an example of one of the Natural Hazard. It's a web application which store information locally on internal cloud platform, and then present it through the web interface to the end user. So this is one of the screen how the Natural Hazard looks like. So far we have imagery, weather information, hydrometric air quality, earthquake, volcanoes, and a landslide. So on a screen, you see the earthquake information in British Columbia for the last month. And the radius of the earthquake represent the depth, and the color represent the magnitude. So the darker the color, the stronger the magnitude, and the bigger the radius, the deeper it happens. Here's another example of the Natural Hazard In this case, it's a weather. So on the right side of the screen, you see the location of the sensors that we collected information across British Columbia. When the sensor it's close to each other, so we're trying to cluster information, cluster all the sensors. And when you click on it, you will be able to see the individual station. And upon clicking on that station, you will see the reading. So on the left top corner, you will see the metadata that represent this particular station. And at the bottom section, it's a graphical representation for the visual appearance. And next is probably the most interesting and related to the topic today. So this is a live feeding of the earthquake sensor, which is called Raspberry Shake. So what it does, it installs a sensor in a various location, and we receive the live time feed into our server. And then we propagate this information directly to our web server and present it on a website. So what you see on a screen, it's between like 1 to 2 minutes delay of the live occurrence. And you can see the different channels. So like in a 3 different direction, like in the north, south, east, west, and the vertical, and you can pick up and select either one of them. So amount of information we receive is enormous. So for one day, we're probably close to 1 million record. So obviously there is a huge performance issue that we've been dealing with, but we found the great solution that allow us to store this information and get access practically any historical information going forward. So if that information is need to be presented, it's easy to pick the date on which you would like to select it, then select your time window. And then during that time, it's more detailed information that may be presented for the viewers. Also, this information can be downloaded in a various format for investigation and future research. So I guess now I just transfer to Jillian to talk about the similarities between natural hazard and HALO projects.
Thanks, Andrei. So yeah, I'm hoping that we can go through the similarities and a little bit about the differences, and then talk more generally about some of the challenges with building these kinds of infrastructures, particularly thinking about the data, the large amounts of data that are going to be streamed in from the hydrophones. So I'll start with the similarities. We've seen this schematic done in a lot of different ways today, but I'll start from the very front, which is the fact that there's lots of different data sources. So natural hazards, like we saw, there's about 5 or 6 data sources. And I think Andrei and the other 2 developers on the team are adding in, seems like a data source like every couple months. So this idea of dealing with lots of different data sources, finding ways to present that information, but also store it on the back end is a nice similarity to have, something nice to already have some experience with, particularly within the context of the computing system that we're going to be using for the for HALO, which leads me to the discussion of the computing system, which for folks who don't know, Simon Fraser hosts a supercomputer called CEDAR, which is, I believe, the largest general purpose academic supercomputer in Canada, which means, one, it means that Andrei and I work, like our desks are beside some of the people who run that machine. They work in our department, which is really nice to kind of have some insider access. But it also means that as since Ruth is a researcher here at SFU, and just for researchers across Canada, there's access to this resource kind of in-house. We have a lot of different resources there, and just, you know, being able to access a supercomputer for free is pretty nice. So the Natural Hazard Project is built on CEDAR, which is what the HALO project is aiming to be built on as well. And then in terms of actually, I skipped over streaming data, but I'll keep going with the data portal and archive. So a nice thing about the Natural Hazards Project, we've already worked through how to build this kind of data portal. How do we allow people from outside of kind of the internal SFU network, outside of Compute Canada? How do we allow the general public to go and download that data, access it, visualize it in some way? As well as how do we store this data? How do we store terabytes worth of data that are coming in? How do we continue to do backups of that data, etc.? Those aren't trivial challenges, so it's nice to kind of have natural hazards as this kind of experience in our back pocket that we can continue to learn from. And just to jump back to streaming data here, so that Raspberry Shake data in particular, if I take a step back and kind of forget what it's measuring, to me that seems very similar to the acoustic data that's coming from hydrophones. It's being streamed in from some field deployment, potentially in a remote location in BC. And we need to find a way to bring it into the infrastructure in near real time or in real time and kind of store it, deal with it, and deal with all of the challenges that is inherent with streaming data. So that's kind of why we think natural hazards is a relevant topic for this audience. But there are, of course, going to be some differences because every project is going to be unique. So one difference is just the time delay. So right now, that Raspberry Shake sensor, Andrei, you can correct me if I'm wrong, but I believe it's sitting on Burnaby Mountain somewhere. So it's pretty close to the infrastructure. It's pretty close to the to Cedar. You guys may have all walked by Cedar on your way here. So these are very tightly linked. So the delay is pretty small. And of course, for the Follow project, there's a lot of different hydrophones, a lot of different systems, a lot of different ways of transmitting that data. And so the time delay, just by virtue of that, is going to be slightly different and probably longer. And the other big difference, this goes to the session with Oliver and Fabio and Val and Paul, is the processing tasks that we actually want to do with that data once it arrives on site. With the seismograph data that's coming from natural hazards, we're really not doing a whole lot. There's some cleaning, some noise that has to be done, but for the most part, end users are seeing that data right away, just kind of in raw form, just visualized nicely. Whereas, of course, with the Hollow project, what we're wanting to do is run a whole bunch of really sophisticated machine learning models on that data before we actually, present it to someone, because we only want to present the data if we're, relatively confident that it is a killer whale or a humpback. So those tasks take a lot more compute energy and time. So we have to find a way to probably build in some sophisticated hardware there as well, which means slightly different systems are going to be needed. And finally, I added another little output there is the notification. So right now, in the current state natural hazards project, there's the goal to have notification, some sort of notification system when an earthquake is detected, but in all reality, we're probably going to have the notification on our phone from the government if an earthquake is happening. Whereas the notification system is going to be a key part of the output from these models is once we get a detection and perhaps, decide that it's in the way of a vessel, or that the movement model might estimate it's in the way of a vessel, then we need to be able to notify someone quickly. This leads to kind of a more general discussion on data streaming challenges and just challenges in general when we're thinking about the computer infrastructure that needs to underlie all of these really sophisticated systems. So the first three are familiar for anyone who's ever heard the term big data, but these are some of the challenges specifically related to the data and just how it's being streamed in. So the volume, the velocity, and the variety of the data. As you all know, there's a ton of acoustic data coming from these hydrophones. The volume is large enough that we have to be really thoughtful about how that data is being transferred across networks, how it's being ingested into a network. How do we make sure that SFU doesn't flag a hydrophone as trying to take down the entire network? Then also just that amount of data that needs to be processed and possibly needing specialized computers to do that. And how do we go about storing that data, creating backups without breaking the system, and really make this a long-term solution. Similar note is the velocity, so just how quickly this data is coming in. If we're receiving, you know, a gigabyte of data every second, we're going to be hard pressed to find a processing unit, a computer that can actually do that processing that quickly. So velocity and volume are quite closely tied. And the third is variety here. So the question is to how many data sources are we actually dealing with? Are all those data sources speaking the same language? Do the annotations that come from, or do the audio that comes from one source, does it align with the audio coming from another source? Is that metadata in slightly different formats? And how do we build a system that's able to take all those sources and allow them to work together effectively? And then the final two challenges I just wanted to highlight is the first one is resiliency. So question as to how streaming and just general infrastructure should handle errors or failures. Streaming data is a little bit different in that it's coming in all the time, and decisions often have to be made kind of in semi-real time as to at what point are we storing that data. So if the network goes down for some amount of time, is that data being lost? Is some portion of it being stored on a device? And how does it make its way to the end, or are we losing data somewhere in that pathway? And the final one is this idea of potentially needing to reframe how we approach the data. Streaming data is a very different context where you don't really have a start and end. You're just constantly being given data points, and you can't really think of it in terms of, okay, I've got my 1 terabyte of data, now I'm going to process it all. You have to kind of think about it in terms of each data point and how do you process it independently of other data points, or what happens if 2 data points arrive in a mixed up order? Is that going to affect the model that you're creating at the end of the day? And I think that's, oh, and then some Halo specific requirements and challenges. I talked about most of these already. Or I talked about the one that I think is perhaps the most important, which is the CEDAR infrastructure. Because we're kind of doing this within an academic setting, or we're using the resources that are available to us as an academic institution and academic federation, we're gonna try and we have to fit into some of the constraints that exist within the CEDAR environment. So that means learning how to fit some of the more general streaming services, streaming softwares into CEDAR and make those work and play nicely together. And then a couple of other ones that are in some senses opposite sides of the spectrum. One is, do we need to have specific kind of security for some of this data? There's mention earlier about whether sightings should be allowed for people to see sightings all the time, or if we need to kind of wait a few hours and then open them up for the general public to be able to visualize. So do we need to protect this data? And on the other end is what data needs to be made openly available to the public. You know, it's one thing to kind of publish a set of data, but if we say that we have a petabyte worth of data that we need to open up to the general public, how do we go about doing that? That's a different kind of, it's a different question, a little bit more hairy. So those are, I'm hoping that this gives a general context without getting too into the weeds of what's going on kind of between the hydrophones and wires that are connecting those to the supercomputer that's sitting up here, but just some considerations.